Good morning. Today we will talk about the story of the universe, starting with the Big Bang. The realm of our knowledge starts with a singularity, a point of which modern laws of physics and mathematics do not apply. We do not know how this point was formed or what it came from. Approximately 13.7 billion years ago, this point started to expand. This expansion is known as the Big Bang. After 10 to the minus 32 seconds, the only thing that existed in the universe were gluons, which formed into quarks. During this period, the universe was only hot plasma known as photon-baryon plasma, where matter and energy were essentially the same. As the universe kept expanding, it got slightly cooler. Cool enough for trios of these quarks to combine into baryons, also known as protons and neutrons. As the universe cooled down even more, the baryons combined to make the first atoms, mostly hydrogen and helium. The first matter. In the next 300,000 years, gravity was able to pull together these hydrogen and helium atoms to form galaxies, stars, nebulae, and planets like Earth. But how do we know this is what happened? What evidence do we have to prove that the Big Bang even happened? One piece of evidence is the red shift of galaxies. By observing galaxies through satellites and telescopes, we find that they appear red. The Doppler effect is the change of wavelength or frequency moving towards or away from the observer. When matter moves towards the observer, the wavelength gets shorter. As it moves away, it gets longer. In the visible light range of the electromagnetic spectrum, the colors blue and violet have a higher frequency. The color red has a shorter frequency. This means that because galaxies are redder in color, they are moving further away, meaning space is expanding as time goes on, which means going back in time would make the universe smaller, eventually going to a single point. Another piece of evidence supporting the Big Bang is the presence of cosmic microwave background, or CMB. When we look into space, we see darkness. Up until the 1960s, we thought space was empty. However, when Penzias and Wilson pointed a satellite dish at the sky, they discovered static. Although they thought it was interference, they accidentally discovered cosmic microwave background. Remember the photon-baryon plasma. The photons in this early stage of the universe emitted wavelengths. As the universe expanded, these wavelengths stretched and cooled, allowing the electrons to stay orbiting around protons, forming matter. Once the universe cooled enough, around 380,000 years after the Big Bang, these photons were able to continue stretching at the speed of light. As demonstrated by the Doppler shift, the wavelengths have gotten redder and redder, eventually getting to red for the visible light section of the electromagnetic spectrum into the infrared, surpassing even that and eventually becoming microwaves. These microwaves were picked up by Penzias and Wilson satellite dish, and even the antennas on early TVs. CMB is what gives the universe a temperature. 2.725 Kelvin to be exact. We can analyze fluctuations in temperature by fractions of a degree from different areas of space, and create a map which shows the temperature, or density, of a large portion of the universe. And because wavelength travels at the speed of light, we can determine the approximate age of the universe, 13.7 billion years. Something any universe origin story has to explain is why 98% of the matter by mass in our universe is hydrogen and helium. Let's travel right after when the only things that existed were photons and baryons. There was enough energy where protons and neutrons could interchange, meaning there was an equal amount of both. Minutes after the Big Bang, the universe is cool enough to start the fusion from hydrogen into helium, doing so successfully. However, to continue fusing, the universe is too cool and not dense enough. To fuse into heavier elements, we will need to wait until stars form. But how do stars form, and how do they create heavier elements? Stars form from stellar nebulas, which are made of plasma, mostly hydrogen, and a bit of helium. All stars are formed from nebulae. From here, they can either be a high-mass star or a low-mass star. Low-mass stars are when the mass of the star is up to 1.5 solar masses, or up to 1.5 times the mass of our Sun. Our low-mass star is now a protostar, which is what our Sun is. When the core temperature gets to 15 million degrees Celsius, nuclear fusion starts. This main sequence star produces light and heavier elements up to about calcium. When the star uses up all its hydrogen fuel, it stops making elements, shines less brightly, cools down, and expands. The outer layers shed away into space, forming a planetary nebula. The core becomes a white or brown dwarf, eventually cooling to the about 2.7 Kelvin of the universe, now a black dwarf that doesn't produce heat or light. This process takes about 10 billion years from a nebula to a black dwarf. High-mass stars, however, are much more explosive. They are from 3 to 50 solar masses in size. They begin like low-mass stars, but since the mass is much greater, the process takes significantly faster. When fusion of helium starts occurring, instead of only forming elements up to calcium, it forms into iron. These elements form in shells around the iron core. When this red supergiant runs out of hydrogen, the fusion stops, and it starts to cool. However, unlike low-mass stars, the star begins to collapse under its own gravity in less than a second. The iron core begins collapsing into neutrons, when suddenly the star explodes in a massive supernova, which for a moment is brighter than the whole galaxy. This hot, monstrous boom is hot enough to fuse to even heavier elements such as platinum, gold, and plutonium. This is the only way that elements past iron are created. After the supernova, if the core survives, it has two paths it can go. If the energy is greater than the mass, less than around 30 solar masses, then it condenses enough to where the protons and electrons become the neutrons. And this solid ball of neutrons becomes the neutron star. If the mass is greater than the energy, however, then the gravity is high enough, and the mass becomes so condensed that it forms a black hole. Due to all this extensive scientific evidence, we can prove that the Big Bang did happen. Thank you all for watching, and I hope you learned something. Goodbye.